Hello, everyone. So it's time. Thank you for coming. I have a lot of very interesting things to share, so I will start right away and not waste much time. I hope to fit it all in. So first, let me introduce myself. I'm Sanne Grinovero. I'm Dutch. I'm Italian. I'm living in London, and I came here because I was invited to introduce this to you. So I'm very glad for that. Thank you. And well, I work for Red Hat, where I'm the middleware research and development area. So like mostly Java. I'm known to lead the Hibernate team. So I've been working for 10 years on Hibernate now. And more recently, we started this Quarkus thing, which started a bit like, hey, can you improve bootstrap times? Because, you know, clouds, they work better if you boot faster, and many other ideas. So while working on that, on all this time, I've been contributing on several other open source projects. So that's a little list. I started contributing a bit on GraalVM as well now because I got really interested in the potential of this project. So what are we going to talk about? I'll try to introduce you a bit about the GraalVM and native images, so what they are and what the problem and like benefits is with them. And that's where we get Quarkus. And then I'll have a little demo of showing you, hopefully, how much nice it is to code on this platform. And I really hope to be able to explain a bit more into detail how it actually works behind the scenes, so what's the tricks and how we actually get this stuff working. So let me start with native image. This is a term I've been throwing around, but it's not always clear. So what is a native image? Let's start with a very quick demo about that. First thing, if you want to try this at home, it's really simple. You will need to download the GraalVM distribution, and then it looks like a JDK. You point your environment variables like Java home, you point it to where you extracted this, and you probably want to put it on your path as well because it has some additional binaries in there which are useful. Then what you do is like you build your application as usual, but then there is an additional phase called the native image, which can convert a jar into a native image, which is like a platform dependent specific, highly optimized binary, which runs straight away. So let's see this directly. So I have a demo here, which is extremely simple. You all know Hello World. So I have a main class here, which is printing Hello World. So let's make a native image out of this. So the first thing I do is, of course, I need to compile my file. So, you know, initially we had this main Java, and now I list, and now we have a main class file as well. Now I need a jar from this, so let me jar this up. CFE, the name of the application I want to run, what's the main entry point, and which classes to include. Now just this one. Okay, let me see if we created a jar. It's there. Now, you know Java, I can run this like that, and it's printing Hello World, right? Nothing fancy or special about this so far, but we can also do this. Native image, jar, up jar. Now this is using the GraalVM compiler to compile this code and all the code of the JDK to build a highly optimized binary, which we can, let me just show you how this looks like. So there is this up binary now. You see this is an executable, and it's 2.4 megabytes. This is a Linux ELF binary. So it's linking directly to some other libraries, and I can run it like that. Hello world. Now another benefit is this doesn't require a JDK. So you just take this binary, wrap it in a Docker or a container, and that's your application. It's ready to go. So that's a native image. The question is, of course, okay, that's Hello World. How do I get it for running more complex applications? And there, well, you need to learn about some of the limitations. It cannot just convert any application and make it a, you know, executable. So let's talk a second about GraalVM. GraalVM is a large project which has several interesting tools in there. Like it has these truffle components, which I'm not going to talk about today. And it's also integrated in OpenJDK, so you can actually run the Graal compiler within the JVM to optimize your code instead of C2. Chris Stallinger explained how to do that earlier in this room. But we are going to focus now on the substrate VM component, which is like using the GraalVM compiler to compile your application classes, the JDK classes that your application is using, and these bits from the substrate VM, which are like their implementation of some components that cannot be ported otherwise. And that's mangled together, extremely optimized by the compiler, and you get this executable out of that. So a big thing about this is it needs to run this static analysis. So this is ahead of time compilation, right? So you're not doing just-in-time compilation like we're used in Java. So it needs to compile everything, which means it needs to also see everything. So that brings us to this closed world assumption. Like when you're building the application, you need to have all the code there, and the compiler needs to be able to see all the code and the possible flows that are going to be executed. There are great benefits from this approach, mostly like that code elimination. So for example, in the demo I ran before, like all the components in the JDK, now we have modules, but modules are very coarse-grained, right? This is looking at method by method, field by field. Are you actually going to need this field in your final image? If not, it's thrown out. Like it's not being included. So that's keeping the memory cost very low, the bootstrap times very low, and just the size on disk, all the resources pushed down to the minimum. So we really like this aspect of aggressive dead code elimination, which comes from static analysis. However, this is also like a, it's a strong suit, but it's also a very weird way to looking at the Java platform, because we are not used to it. And all the libraries we're running and all the platforms we're running make assumptions on the fact that it is a very dynamic and rich platform that you can do stuff, generate code at runtime and do interesting things. So these limitations brings us to, you cannot have dynamic class loading. In practice, if you try to get a reference to a class loader or your current class loader in the context of something, you get a null back, a null reference, which means most of the libraries out there will throw some random null pointer exceptions there, because they might try to do something. Nobody expected this when writing this code, that it could return null, but now it's returning null when it's compiled. So this also implies you cannot deploy jars and wars at runtime. We have all been used to, you start with Tomcat years ago, and then you produce a war, and then you load this kind of multiple wars are like plugins of your container, and you load these things dynamically. That's not possible, because this is violating the principle of the compiler needs to be able to see all the code so that it can actually prune the dead code, right? How does it cannot know what it can remove if you are allowed to introduce additional methods which might code, invoke things, methods, JDK methods, or use constants, which he actually removed upfront. Another thing is, well, the management extensions and the tooling instrument, the interface are not available, which means no agents, which means no JRebel, no Byteman, no profilers, no tracers. So this is like killing a whole area of very interesting tools that we are kind of used to. And no Java debugger, right? You cannot use the JVM debugger to connect to one of these native images, because if you didn't tell him that you're going to use these kind of things, the infrastructure to support this stuff has been thrown out to save more memory, save more disk. Now, of course, some of these things can have flags that you enable at build time, and that makes the compiler behave differently, so that some of these things are not thrown out because you might want to do them later. But you have to tell it explicitly. Other areas is like no security manager, and we're like, woohoo, finally, because that's very complex to handle, but also like, why do you need a security manager if nobody can actually load new code in there, right? And there is no class loader. No finalize support, which is great, because it's been deprecated by years, and now you just cannot really use them, so you folks. This is a bit of a sore point. Like invoke dynamic and method handles have only very limited support, so if you're doing crazy optimizations based on invoke dynamic and method handles, there's a good chance that this will not compile to native either. And why is that? Again, because you are generating code essentially at runtime, right? So that's, again, a violation of the closed world principles. Reflection. Now, if you allow reflection, again, the compiler cannot see which fields are you going to read, which methods are you going to invoke, and so on. So reflection is not allowed, except, of course, if you explicitly tell the compiler, look, when you're compiling this, can you, keep in mind that I will invoke reflectively, like, for example, this one constructor of this class. So if you tell it that upfront, it will just keep the infrastructure in the image so that this is then going to work at runtime. But if you forget one of these things, it's not going to work. Of course, dynamic proxies, aspect-oriented programming, interceptors created at runtime, loading resources, or using GNI, unsafe memory, all of these things are not available either unless you hint the compiler, look, I have specific needs, I need this method to work in these conditions, and then it can fold this information into the optimization decisions. But again, it's an opt-in thing, you have to tell it. Now, the static initialization is another interesting aspect. This is a very special behavior. Essentially, every block which is static in your code, which means also like simple constants, like you have a public, static, final, string, and then there is something there. That's the static initializer. You know that when your application is initializing this class, that string is created at that point, right? Now, what's happening here is that this string is actually created during the compilation of your application. Now, it's not just strings. It's like every more complex static block that you might have, every more complex objects that you might be initializing is run, the code is run within the context of the build, so the compiler is running it. It's actually checking what kind of code you are including in your static initializers, because some things are not legal, and we're going back to that later. But essentially then what do you get? Like these things that we look at, they look constants when you're reading the code, right? We know they're not really constants because we have the reflection API. So you can say, well, I said that's the final field, but let's make it writable again, remove the protections because my library needs to do something odd, so I'm going to change it again. So in the JVM, all these things are allowed, and they kind of have backdoors. You cannot allow these backdoors to run in GraalVM because that would like mutate the constants, which are strong assumptions that the compiler again is going to use to optimize your code like crazy. So in a way, I prefer this. Like if it's a constant, it really is a constant, and the optimizations behind that are quite strong. So what happens is these objects that you created during the build, we take a snapshot of that memory, and that's compiled into the native, and that's already initialized, ready to go. Like this goes in the constant pool of the binary. And there it goes. So among the things that are not allowed to run in the static initializer is, of course, like if you try to open file handles, sockets, or start background threads, like there are many things that need like a timer that's started in background to do some periodic things. If you do anything like that, the GraalVM compiler actually sees through that, and that's a violation of the rules. Like, of course, you don't want to start these timers within the compiler. You want to start them in the end application. So in these cases, to be fair, this is changing right now in master, so I'm not sure what direction we're going to do, but it seems the idea is that rather than failing the compilation, it will automatically detect that these blocks will not be run during the build and they will be run later. But this is a change of how current GraalVM latest release is, which would just fail the build. Like you're not allowed to do this in a static initialization. And you can explicitly opt in yourself to like defer the initialization of a specific list of classes. Now, of course, so these three are illegal, but you have to be careful also with other things. Like, so if you're like having in your constant, like you're taking like the current timestamp because you want to know when this application was booted, well, that timestamp is actually going to have the timestamp of when this application was built, maybe on a different machine. Maybe years before it was actually started on this new machine. Now, you also don't want to capture environment variables or things like that. System-dependent constants, I mean, like if you're doing optimizations based on the number of CPU cores your system has, you might be capturing the number of cores that the system has when it compiled your application, which is not maybe what you really meant to look at. So you need to be careful at what these static blocks are containing. And so when I mentioned you need to disable some things like JMX is not supported, let's take some examples from the Hibernate library, which is where we're going into, right? So in Hibernate, you can enable the management bean via some configuration attributes, and that allows you to look at statistics like what's my slowest query, what's my query ratio, and all kind of other metrics. They are registered in this management bean if you enable this in the configuration. Now, the code then will look like, at a very high level, it will look like this. If it's enabled, then we register some things on the management bean. Now, this code will not compile because the register JMX method will do something which invokes this API from the management beans, which is a violation of your reachability, like you're reaching into code which is not implemented, so no way to compile this. And of course, the compiler cannot see that this flag is maybe off in your specific configuration, because what will this binary do when you actually enable this in your configuration, right? It needs to know what to do in that case. So the correct way to disable a feature is to have code that looks like this. You have to have a constant which blocks any flow of code to go into that method. Now, when the compiler sees this, and reflection is not allowed, so this is a real constant. This is always off. So this method will never be invoked. It's not even compiling it. Right? The whole code is going to disappear. So the trick is you need to make sure that it looks like that. Now, that's where we are getting at. So you need to adapt your code so to make sure that the code flow that you're having is really, legal code, not having these assumptions that are no longer valid. So you could, it's not that much work for your library. The big problem is you need to compile all your dependencies as well, right? Because everything is going to be compiled into and optimized into the single binary that's representing your application. It's not just your code. So that's really all your dependencies, like your dependencies and the dependencies of your dependencies, like everything that you have on ClassPath, including the JDK, is included into this. So that's a lot of code that you need to probably verify that it's behaving like you're expecting. So what's the impact on Hibernate? Now, I'm taking Hibernate here first off because I ported Hibernate to Quarkus myself, so I can answer very deep questions about this. But what we learned about porting Hibernate to GraalVM can be applied to all the other libraries. Just so it's interesting to discuss Hibernate because it does pretty much all the illegal things that we are seeing here. It does them somewhere. So we had to figure out how to have an alternative plan to make sure that you can have all the benefits of Hibernate, no trades-off, and still compile your application to native. So let me switch to a mind map here. So this is pretty much the steps that we needed to do, right? So let me just select some. We don't have to discuss all of them, but so for example, resource loading. You might have an import SQL script that you want to be imported in your database when your application is run. This is mostly done for development, right? But some people do it in production as well. So you need to have this resource included in the binary. And that's what the Quarkus Hibernate extension will do. So if it sees that you're importing this by just parsing your configuration, it will include this resource in there. Easy. Now, no support for JMX. You have seen that before. Well, it's just disabled in this specific code, which is generating the bootstrap of your application. It's making sure that the compiler can see that this flag is really off, and there is no way for you to enable it. Same for Security Manager and securities. And then, well, of course, there were some libraries that were starting threads in background on class initialization. Now, that's a bit dodgy anyway, so I just patched it to make sure that doesn't happen again, and that's resolved, right? But then, so reflection. You might assume Hibernate does a lot of reflection. In fact, it doesn't have to. There are alternative ways that it can enhance, mostly for performance reasons, it can enhance access to your entities. Now, it turns out that using reflection on GraalVM is actually super efficient because the GraalVM, as soon as you tell it, I'm going to do this, it's not really using the same code. It's just, shortcutting the whole operation. What's missing here is you need to register the reflective needs of your application. So all the entities you have, all the constructors of these entities, the accessors of these collections, the getters, setters, all these methods that the framework needs to invoke or read need to be registered in a configuration file for the compiler, which is to say all of this stuff needs to have reflective access. Now, if you are not using Quarkus, you can use a JSON file and just list all of that stuff in there. But it's very tedious. So what Quarkus is doing is literally, well, I know your application. You're not allowed to mutate it later. Right? So you're not going to deploy additional entities later. You're not going to instrument it. So we're just looking at your entities on the class path, and that's the list of things that we automatically then register into the compiler. Like, so there is a callback from the GraalVM compiler into the Quarkus framework, which then delegates to all the frameworks that are integrated within the Quarkus build. And each of them can list, okay, I'm going to search for like JPA entities. These are the classes I will need to have reflective access for. And then you're good to go. The compiler knows this and it's folding this information in. Now, well, another thing we had to do is, well, on dependencies, so all the Hibernate dependencies have been kind of converted to run fine on GraalVM. You know, a big one was I need to convert even the JDBC drivers. So Postgres SQL driver had some issues initially. First off, it does, well, internal reflection. We patched this to not do that anymore. It uses phantom references, which used to be another thing that's not really allowed within the GraalVM, but actually this is out of date. Now phantom references just work fine within GraalVM. So, but you know, there was a patch for that. And yeah, and then you discover interesting things like the Mariadb Driver. When it's authenticating to your database, it's actually initializing JavaFX in background. Did you know that? I had no idea. So every time I ever connected to MariaDB or MySQL, you have additional memory consumed by your JDK because it's initializing all of the Swing, Java 2D, and JavaFX classes, just because in the security options, one of the ways to connect to get the password is to open a dialog box and show you the dialog box. Right? Now, even if you're not using that, that code is still being initialized and triggers the JVM class initialization in a chain. And that's just an example of all the things we had to do to get there. And now, of course, Hibernate also needs Antler to do the parsing of your queries. It needs a transaction manager. So the Narayana transaction manager, which is, it's probably better known as the JBoss transaction manager, was also converted to have a Quarkus extension and work there. XML parsers need to work. A connection pool, and so on. Caching. But let's go to the more interesting things. So Hibernate cannot create proxies to do lazy initialization of your entities. And it cannot enhance your entities at runtime. Now, if you are very familiar with Hibernate, you might know there are also plugins for Maven and Gradle and Ant to do class enhancement of your entities at build time. So that's what you're using. Technically, all your entities are being enhanced before the compilation phase to native. The interesting fact is you don't have to set up these tools anymore. What you do here with Quarkus is we already set up all the tools automatically so that all the classes, when they are inspected for your application, then we know, okay, there are JPA entities here, let me enhance them. And then, it's the enhanced version of the class that's then being put in the jar with all the other enhancement that Quarkus is generating, and that's then later compiled to native code. So there is no dynamic class loading, there are no proxies, there is no runtime bytecode actually happening in your application because it was already done before that, right? Now, another aspect of this is like you don't really need to do class path scanning. This is probably this is the slowest component of booting Hibernate. When you're starting it, it needs to find which are your entities in your model. Now, to find them, we need to look for, JPA annotations in all your dependencies to figure where they are. Now, this stuff can be done at build time, right? And then there is no need to repeat it every time you're starting the same application. Since we're talking here about, microservices or immutable applications and not servers that are behaving like a container in which you can dynamically add or remove code, then everything is known during the build. Like as you are looking at your code and you know which entities you have, so can the compiler look and see what are the entities you have, and that's a constant. As soon as we have these constants are literally generated as static initializers, constants in classes which are dumped on disk, and this is additional code that's been included in the compilation of your application. Now, when we have these constants, this can actually optimize the size of the whole application like crazy. If I can see that in your entities you are always using a specific ID generation and you're not using any other ID generation, then these other ID generation strategies, which are in the Hibernate library, they are getting removed. If we see that you're compiling your application to connect to a Postgres database, all the code that we have to support Mariadb, Oracle databases, and all the other stuff is removed. That's because you can now rely on these constants after the build. I hope that makes sense. Okay, this area is also interesting. So what we're doing even further is we can start Hibernate within the compilation. So when you're compiling, I'm bootstrapping Hibernate, up to the point that it needs to connect to the database. We don't want it to connect to the database because you're compiling, right? So maybe you don't even have the password to your production database, or it's not reachable from this machine, right? But we can, so what we did is split the phases within the framework so that we can get to a point in which all the metadata about your application has been computed. We have all the entities, we have them all enhanced, and all the code that's ready to initialize it has been run. Then we take a snapshot of that, and that's what's included in the binary. So all that work doesn't have to happen every time that the application is run because it's already done. The only thing that's missing is, okay, now you really can connect to the database and we get going. And well, the same approach can be applied to all the other frameworks, right? So the important thing is that you can reorganize the code into this phase, which is not what Java developers usually do. And then, we snapshot that, and that's the state of your application when it's meant to run. So this is like the introduction to Quarkus. So what is it really? It's a bit of a toolkit and a framework to start your application. We're focusing on Java applications, of course, and a little bit on Kotlin as well. So like exploring it, it looks interesting. So far, there is an extension for Kotlin too, so if you want to play with that. And it's really designed to be really light and aiming for cloud environments. And well, it's designed upfront thinking about the problems of GraalVM, right? Now, what I really like is like these limitations of GraalVM, they become almost like a strong point. Like since we can really rely on these constants and the dynamic aspect is gone, then you can optimize even further for everything. So this is how it looks like in terms of process. Like you have your application, which gets compiled. Then the Quarkus build plugins, there are for Maven and there are for Gradle. They work in pretty much like they inspect your application. So I can see if you're using Hibernate or not, and which entities they are, and we can enhance them, apply some additional magic. And that's done an optimizer jar, a very highly optimized jar representing our application, which can run on the JVM. And in fact, it runs on the JVM, consuming far less memory than everything we had before, because most of the work was done at build time, right? Since we're moving into this idea that one application goes in one JVM and it's not really changing, like when you want to have a change, you just build it over, and maybe you create a new container and replace the old one. It means that all of this work that we're used to do during the initialization of the framework can really be moved into the phase in which we are creating the application. Now, of course, you can go the GraalVM way and build a native executable as well. Now, the interesting thing is, like I said before, you cannot use the Java debugger on the native executable. But since it's the same application that you can run on the JVM mode as well, if you have a problem with your business logic, you just run it on the JVM and you work as usual. It's just consuming less memory and booting in way less. So it works via these extensions. And we need for all of these frameworks that we're supporting now, they need one extension to support it. So all the stuff I showed you on the mind map for Hibernate, we did that for several other libraries. And you might want to add some for additional libraries that you need, right? So they do multiple things. One of them is, of course, to make sure that the library becomes compatible with the native image of GraalVM, but that's not the only goal, right? Quarkus is very interesting even if you are not planning to run it as a binary. It can, we'll see some more benefits now, like the development hot reload capabilities, live reload capabilities. And it just takes way less memory in JVM mode, right? So these are some of the libraries that are supported now. There are actually many more, but these are highlights. So you might see Kafka is quite good now. Well, Hibernate, REST-easy. Well, Undertow is here too. It's not on the list. Netty, Vertex, and we're heavily focused on Kubernetes going for OpenShift, and Infinispan, Prometheus, the whole thing. And there are many more coming here. Another goal of Quarkus, in terms of more like a platform, is to expose, in the ease of use world, it's going to give you an API which is for imperative and reactive, which look similar, so you can mix imperative and reactive coding, like the REST-easy and the Vertex things, they can be used reactively. But I'm not going to talk much about this today. Now, with this goal of being container first, well, we have seen the size on disk becomes really small. The boot time is much faster, which means you can really scale up your instances on clouds, on Kubernetes, without worrying too much about all the time it takes to boot the whole JVM and the warm-up of application of the JVM, because everything was pre-compiled. So you can have your full application started in milliseconds. And we're looking at memory consumption, but we're not really looking at heap sizes anymore. That's not really interested in Kubernetes. What we're looking is the total resident set size consumed by your application. So what is that? That literally is the sum of all the memory regions that your application is consuming. So it's not just a heap. It's your heap, of course, but also all the other costs that the JVM has when starting. The more threads you have, they all need a stack. That's one region. Then you have the metadata of all the classes that you are including. So the less classes you have, the less metadata. So all the dead code elimination helps there too. And of course, the compilation, the just-in-time processes, and all these things that need to happen in the JVM, they are consuming additional memory that you don't really necessarily see in the heaps, right? But if you're breaching your RSS limit on the cloud, your application gets killed. So it's important for us today to focus more on RSS than heap consumption, even if heap consumption matters as well. So this is how we measure memory. We'll see that in a second. But so how much memory does it consume? So in a REST application compiled to native, the total memory consumption is about 13 megabytes. This is with 1 megabyte heap, right? So that gives you an idea that you really need to look at the whole thing, not just at the heap, which is just 1. Now, the whole memory consumption on the same application running on Quarkus on the JVM is about 74 megabytes. If you try to beat that with any other framework out there today, you're unlikely to get below 140 megabytes. So we can say that both of these are running on the JVM traditional, not GraalVM. Right? So the savings in memory are very strong. Now, a more complex application, which is using Hibernate as well, which includes a caching library, connection pool, transaction manager running, well, the GDBC driver, and a lot more. The memory consumption is still very low, and super competitive even compared to other frameworks. Now, startup time, let's just skip, but let's skip to the time it takes to run. So this same REST demo in native will start in about 14 milliseconds. On Quarkus, it's still, so JVM, it will run in less than 1 second, and in a different cloud stack, it will be at least 4 seconds. With JPA enabled, it gets a bit slower because, you know why? It doesn't actually get much slower at all, but it's also connecting to the database, filling the pool, so it's like multiple connections being authenticated to the database, creating the schema and all these things. So you can boot in about 50 milliseconds, including Hibernate and the transaction manager, everything. On the JVM, it's 2 seconds traditional, it's getting close to like 9-10 seconds with this specific demo we had. So developer joy. Let me show you this. So there is this comic on the website. It's pretty good. It feels a bit like coding on PHP. You make a code, your code change, and you just reload it in the browser, and the code is there already. So how do we do that? In practice, the point is, since it is becoming so light and fast, we can actually reboot the whole application from scratch. Right? So when you're refreshing, we reboot everything. And there is no drawback. So let's have a look at this small demo. Here, just have a look at the POM file, how it works. So I'm importing the Quarkus BOM, and then I have some extensions, the ORM extension, the connection pool, or STZ, and Mariadb Driver. I have a Mariadb Driver running here. This is in Docker. And this application has one configuration file. That's the Quarkus configuration file. So it has mostly just data source properties and telling Hibernate that it needs to drop and recreate a database every time it's restored. I also want to log SQL statements, but just to see what it's doing. We have a default import SQL statement. You might be familiar with this. And then there is a page. And then there are just 2 classes in this application. We have, this is a REST easy entry point. So we're exposing a REST API to like load all the fruits, and then load a single fruit, create a fruit, update a fruit, and that's it. Note that you don't need anything else. So since we can inspect your application, then we can infer what you're needing out of this, and nothing else is needed. And then there is one entity, the fruit entity. So this is using auto generation for IDs, and it has a name, and it has a unique name. And that's it, right? There is an entity here and note a named query. Now, let me just show you how it looks like. This is, well, how it, oh, sorry, I didn't run it yet. So if I refresh this, that's dead. Now, I have some terminals here. Maven, package, skip test. No, well, just let's let it test as well. And let's have it package first. So it just runs a build. It will create a jar file. I'm a bit short on time. So it ran those tests. It connected on my Mariadb locally and verified we're good to go. Now let's set Quarkus in development mode. So now it's, okay, well, it's running the tests again. And then it started. So is it started? Yes. So this is how it looks like. There are apple, banana, and cherry in the database. We can like remove some, and we can add some new fruits in the database. Yeah. Now let me just show you this table as well. Oops, not drop. So show tables. There is a fruit. Oh, let me remove the sequence because it's not there yet. So there is a fruit table here. Show create table fruit. Of course, it has an ID and a name, which is a primary key, and there is a unique index on name. Yeah. Now, if I want to go and make some changes here, we can say like the unique needs to go. Let me just switch it here. And then I go here, I refresh this. You see the lowest terminal had some noise here. Let me expand that. It did a hot replace here. And if we now switch to this one, show the new fruit here, the uniqueness is gone, right? So you can have live changes on your entities included. Let's add well, actually make it public. Public string. Let me add the field. I refresh here, it's restarting. I look at the table again, and the new column is there. Yeah? Much funnier to work with this, and it works with anything in your application. So if I want to get, let's say, add something here, pineapple on 4, I save this, I refresh, and pineapple is there. So you can change really anything except the dependencies, because dependencies need Maven to rebuild everything. But if you're not changing dependencies, you can, this is much safer than existing tools which try to connect and use agents to replace some component because it was too heavy to reboot it. Now it's very light and we can reboot everything. So it's the same as killing your application and starting it over again. So that's the live reload capability. And let me quit from the dev mode. Now the other alternative is we can build a native. Now this is going to take some time. We just have 4 minutes left and I think it will take 4 minutes to build. So it ran the test first, it's created the jar version, and now this is starting the native image phase of the build of Quarkus. Now let's have a look at the log here. So it's invoking native image with a ton of special flags, but that's not all what Quarkus is doing. Like Quarkus also generated in the previous phases a bunch of bytecode which is then stored in disk, and these are like all the callbacks that the compiler is running. So one thing you can see is, so this is the compiler, right? But here, this is booting Hibernate. This has selected the dialect and it's like started the transaction manager and XNIO and some other technologies. They have been booted within the JVM context of the compiler phase. Let's have this go for a while I'll try to show a bit more. So yeah, in a traditional app server, when you're deploying something, there is a lot of stuff that needs to happen. Like, so take again the Hibernate example. You need to parse, say, the persistence XML file. Now, just parsing that XML file, that needs you, it's cheap to parse a single file, but before you can do that, you have to initialize all the classes of the JVM that enable the XML parser subsystem. And that actually takes a lot of time for the first time you do it. Now, within Quarkus, the XML file is not really parsed during the runtime. It was parsed before, which means the XML parser implementation of the JVM is not included in your final image because it's not really needed anymore. And it's the same for anything related with annotation lookups. Like, we're not really reading your annotations at runtime because they've been run, they have been read before at build time. And even just validating that your model is fine and all of these things. Since we run Hibernate within the compiler, it would have failed. You would have got feedback about invalid code already. And yeah, so all what we do is then record it into bytecode, and you get a static initializer or a main depending on what the specific framework needs to do. And let's go back a second to see if that was done. It's still compiling. Yeah, it's a very heavy process and it takes a lot of memory, which we can probably see here. See, this is a poor dual core machine with hyper-threading, but it's taking my 4 hyper-threaded CPUs to the extreme. And I don't have more than that memory, so it's trying to use all of it. I should probably kill the browser to get it a bit faster, but we should be almost there. Let me finish with the slides. So the architecture within Quarkus is working with these main components. So there is the Graal SDK, which allows us to have these callbacks to the compiler and enable flags or make sure that a specific class is initialized later before or with a special flag. And Gizmo is a new library we created to create this bytecode that's being dumped on disk and compiled then later. Jandex is an indexer. It's a super fast and efficient way of finding your annotations without initializing those classes. So with Jandex, we scan and have a very good picture of what your application is meant to do and which annotations are there, which technologies are being used without needing to initialize it all. You have seen hot reload goes into action in milliseconds as well. So that's not in native mode, right? Consider that during a hot reload, we need to also rescan your whole application again. So that's fast because of these other technologies. And then there are extensions for all these other things, like every different library has its own extension. And yeah, the purpose is both to work around the limitations of Graal, or let's say take advantage of the limitations of Graal, but also optimize it for JVM mode. And yeah, all the code needs to split very cleanly between what's being run during the build, that's one thing, and what's being run at your runtime. They're different to the point that we have different dependency sets. The dependencies that you need at runtime are a much trimmed version of what you actually have during the build. Because if you don't need it later, but just for build, then it can go. We said this, and that's where we are ending. Okay, build success. That took, well, 3 minutes 38. Now, what do we have now? We have a binary in my target. You see this? Well, we have the jar, which is the normal executable. Let me start that one first. So that's a Quarkus application ready to run in a JVM. So -jar demo2 runner jar. And it connected to the database, created a new schema and all that in less than 2 seconds on my very poor laptop. Now, if we do the same, but without Java, we can run that other executable we have. Runner up. That's 6 milliseconds boot time. And this is the same application, right? This is using REST-easy, Undertow, Transaction Manager, Hibernate, connection to the database, and everything else. But I think the most interesting part really is this code. This code is following the standards and the libraries you're already used to. Right? So there is not much new to learn for you to how do I get working with this technology. Well, this is the usual REST-easy with the standard annotations. And this is totally just a standard JPA. And we just can convert everything to that, to the native thing. So let's just test this application. Well, oops. Is it really running? Yeah, and you've seen here it's logging the queries, right? And I can make the same changes as before. Now, of course, I can't live reload now because this is a binary. It was highly optimized to do what it is doing. How much memory is this taking? This is consuming a total of less than 40 megabytes, but that's total RSS, right? It's not just heap. In fact, how much heap is this using? I'll kill it. Oh, that was the wrong one. I'll kill it. XMX 1 megabyte, will it work? Yep. So it's using 1 megabyte heap total for a total of 40 megabytes application, and that's the same user application. Sorry, my time is over, but I think we can have some questions. Yeah.
I think you kind of mentioned on the beginning, when you start adding new libraries and dependencies, who is going to do the work of adapting to Quarkus? So for a JSON library or something else?
So it depends on how complex the library is, right? So I did the work on Hibernate because I know Hibernate very well internally. So obviously that was a difficult task. You wouldn't have done that in a day. Now, But also, I don't expect most libraries to do all this crazy stuff that like a framework like Hibernate is doing. Right? So many libraries, if they're not doing reflection, if they're just using reflection, it's just a couple of flags. If they're doing weird things during static initialization, then there is a single flag to say, well, that flag needs to be run at runtime. So it really depends on what the library is doing. I think the good news is the GraalVM compiler is extremely thorough. It has to, it's analyzing all the code flow paths, so it knows every possible action of this library, and it will just fail the build, telling you there is this illegal thing that I found in this method over there, and you get an error, and then you will need to make an extension for Quarkus or ask somebody to make an extension for Quarkus, pretty much. Yeah? Thank you. Sure. Thank you.